Good morning, student. I welcome you in a new series of lectures of M.Sc. third semester chemistry. And from today, I would like to deliver a series of lectures on photochemistry. As you know that photochemistry is a very important concept of the chemistry, and it consists of different life processes, several photochemical reactions, and various laws. Before I start my first part of photochemistry lecture, I would like to share about your course content. Now, as you know that the name of the course is CH301, and title of that course is spectroscopy, photochemistry, as well as the most important concept you know, that organocatalysis. But I will concentrate only on unit number 3, that is photochemistry. Although there is a very good relationship between the photochemistry as well as the spectroscopy, unit number 1 and unit number 2 based on the spectroscopy, and unit number 4 is the organocatalysis, and unit 3 is the photochemistry. Now, again, if I dissect the course content, as you know that I have divided your whole course content into 3 subdivisions. Whenever we start any topic, we must know the fundamental concept of the photochemistry. And as name itself is a definition, we must know the definition of the photochemistry. And what is actually photochemistry? And what is the contribution of the Einstein treatment of absorption and emission phenomena like that. So, in first part, I will discuss the interaction of electromagnetic radiation with the matter. Now, second part is also very important. That is called the reaction mechanism. How we figure out various reaction mechanisms, diabatic process, adiabatic process. And third part, there are very important photochemical reactions. You all know all these things like Barton reactions, photophase rearrangements, and there are so many other reactions is also there. And another aspect is, in fundamental concept, photophysical processes. You know that when there is a interactions, there happen different types of photophysical processes. So under this process, we will also study the Jablonski diagram and so many other things, phosphorescence, fluorescence, and so many things, intersystem crossing. And another very important concept, you know, that Stern-Volmer equation, quenching and other things. So this is in short the concept of your course. But today I will, in first part, I will only consider the fundamental of the photochemistry, and in part 2, I will discuss this part, that is the derivation of Einstein treatment of absorption and emission radiations. Now, as you know that although we are living in the digital age and there are large number of information available in the website, and I know that you are all referring the e-Pathshala or various NPTEL course content, but in addition to that, I request all my students that you must visit the library and refer some of the very good books, and some books are also available in digital platform. And my most favorite book is one of the best book, that is called The Fundamental of Photochemistry by K.K. Rohatgi Mukherjee. And Professor Mukherjee was a renowned photochemist of our country, and she was in Department of Chemistry, Jadavpur University. And now there is a society, you all know that Indian Photobiology Society. Headquarters is Kolkata. And another book I always refer, the Photochemistry Past, Present and Future, Springer by Albini. That is also a very wonderful book. And if you want to know some applications and other parts of the photochemistry, Oxford publishing, that is the Photochemistry, Richard Vane and Carl Vane. That is also a very good book. And for application part, because there are two types of application. One is sometimes inorganic photochemistry and large number of organic photochemistry is also there. So that is called the principle and application of photochemistry, Brian Watley. There are other books are also available, but I have, for my series of lecture, I have referred these books. In addition to that, I have also referred some of the research papers and internet connectivity. Now the first point, although from B.Sc level you are studying the photochemistry, quantum yield, you all know different photochemical reaction, but again I must tell you that in one sentence, the study of any type of chemical reaction or any type of transformation where light is responsible. Now there is a question, because if I see the whole electromagnetic radiation from gamma rays to radio waves, there are various sections. But I have seen and I have referred some of the literature, yes, influence of light or the interaction of the photon with that atom or molecule, but that particular, I will explain why that visible and some ultraviolet part is responsible for such type of transformation. And it studies how molecules absorb light energy and undergo chemical changes as a result. There is a transformation. The most important example of photochemistry in our life, you all know that photosynthesis in plant. It is a chemical reactions, because sunlight triggers a chemical reactions where carbon dioxide and water form the glucose and the oxygen. That is the most important reactions. And another reaction is the photochemistry of vision. What we are seeing is one of the most important example of photochemistry of the vision. And nowadays you know that everybody is talking about the hydrogen generation of green hydrogen and other things, photolysis of the water. That is also a most important example of hydrogen generation by the photolysis of water. I will not go into details about all these applications. Just for curiosity, I am just giving some of the examples. Now sometimes there is a confusion regarding the difference between the photochemistry and spectroscopy. And there may be some confusion between the role of classical physics and quantum mechanics. Again, there is some concept about the quantitative measurement as well as the qualitative measurement. So actually, if I see the history of this photochemistry or this spectroscopy, actually, if you in the early 1900, quantum theory, I will explain in my next lecture how the Einstein contributed on this photochemistry concept, and now photochemistry can be explained on the basis of the quantum theory. Although classical theories also help, because when Einstein explained that how light can cause electron to move, which is a very popular thing, that is called the, you can see it, photoelectric effect. And there are two laws, very briefly I will explain all these things, that the Stark-Einstein law helped measure how light is absorbed. That is the one important thing. And of course, there is a tremendous development in the photochemistry. You all know that I think in 1967, there is a Nobel Prize, of course, collaborative Nobel Prize on fast reactions, and you all know the Norris reaction. So Ronald Norris and George Porter, they actually studied the fast reaction and the discovery of the fast photolysis. And recently you all know that everybody is working on the material science or nanomaterials or semiconductors, fluorescence and other things. So now photochemistry has tremendous application, around application in various medical field, photodynamic therapy, and creating a better solar panels, you all know, perovskite solar cells and other things. There are some introductory part of that photochemistry. Now, this very simple question, sometimes asked in the interview and other things, what is the difference between the photochemistry and spectroscopy? Again, I am just referred the book of Professor Rodge Mukherjee and the fundamentals of photochemistry, because if you just see the simple definition in both the cases, whether it is a photochemistry or spectroscopy, there is a interaction between matter with the electromagnetic radiations, or if I complete see the electromagnetic spectrum. But these photochemistry and spectroscopy both involve the same thing. But as a matter of fact, their goals and outcomes are fundamentally different. In photochemistry, there is a formation of the products or other things. But in spectroscopy, there is excitement, there may be rotation, there may be vibrations, there may be different things. But they are intimately related. But what I am thinking that if I see whole electromagnetic radiations, as I have already written here, from gamma rays to radio waves, different wavelengths, frequencies, energies are different. But photochemistry confine it to particular range. You can refer some any other books, you may agree with me or not, but where I have referred some of the books, I have seen that, of course, visible region is definitely photochemistry, 400 to 800, like that. But in somewhere I have seen that the range is maybe 200 nanometer to 750 or 800 nanometer. Now, what is the reason behind that? Because if I compare with any thermal reaction and photochemical reaction, for thermal reaction we have to increase the temperature and energy of activation is required. And there is a bond breaking and making process. So similarly, if I have to break a bond, I need certain amount of energy. And for most of the chemical reactions, there is a general range. I am not saying this is the complete range, but suppose I have to break a molecule, so I need certain amount of energy, that is called the bond dissociation energy. So suppose that bond dissociation energy is 150 kilojoule to 600 kilojoules. So that means if I want to convert or transform or chemical reaction from A to B or AB, I have to break the bond. So from where I get that energy? So then the photon plays a very significant role, because we all know that suppose I need 150 kilojoule of energy, and the energy of photon, the bundle of quanta is equal to h nu, and that is also h, c and wavelength. So such type of, I will show you some of the example where I will show that I have to calculate that one quanta or one Einstein or one photon, which is equivalent to that type of energy. And why I am saying that around 200 nanometer to 750, or in some books it is 800 nanometer, because when I calculate the energy in terms of wavelength, I will get that amount of energy with that particular wavelength. So these energies are available from Avogadro's number of photons of the wavelengths. So again, I have seen that simple formula that you see the range is 200 nanometer and 800 nanometer. And you can refer any research papers or any books. There may be slight variation. Maybe in somewhere is 200 to 750 like that. Now I'm just giving one or two examples. See, just suppose I'm giving a calculation to the student that you can take any molecule, maybe anthracene or any molecules, and take the lambda max like that. It is a hypothetical calculation. Deliberately I have taken 390 for it is a hypothetical calculation. You can take any compound. So a molecule has absorption band with a maximum wavelength is 397. You can take 200, you can take 400 nanometer, 500 nanometer. What I just suppose that type of photon that is 397, so I have to calculate the equivalent energy for that. The energy equivalent to that wavelength to break that bond. So suppose this is 397, you know that I converted into meter, nanometer to meter, so 397 into 10 to the minus 9 actually. So calculation is very simple. As I just told you that E is equal to H Planck constant we know, frequency, velocity of light and wavelength. So you all know that the Planck constant 6.6, I am using SI unit. So 6.625 into 10 to the minus 33 joule second multiplied by 3 into 10 to the power 8 velocity of the light meter per second and divided by this 397. Why I have taken 397? I want to get a 5 just for a student. 5 into 10 to the power 19 joule per photon. So you just remember this thing. Now I am talking about the photon. Now an Avogadro number of photons is known as the Einstein. The amount of energy absorbed to promote this molecule to the first excited state. So, and that is called, suppose if I write E is equal to h nu 1 photon, but if I consider, because every substance contains, the Avogadro number, 6.023 into 10 to the power 23. So that if I just multiplied with that thing, because that is 1 in h, that is actually Einstein, one Einstein. So what I do, whatever I am getting the energy value, I have to multiply with that Avogadro number, that is that photon per mole. And when I calculate these things, I am getting 301 kilojoule per mole. So now if I want to just break this, any type of chemical transformation, and energy is required, so that much of energy I am getting from that photon, one Einstein. So therefore we have just fixed that photochemistry, and this is the difference between photochemistry and spectroscopy. So just to summarize, the students from school level, you are just, again I am just saying these things, photon, one quanta, one molecule absorb one photon. You know that if I see the first law, Grotha's dropout law, which is a quantitative, not a qualitative treatment, that without the molecule has to absorb photon for any chemical transformation. But then actually Stark and Einstein, that is laws of photochemical equivalence, then of course 1 mole, 1 photon, that concept is there. So 1 mole of substance contains Avogadro number. So 1 mole of quanta It must be 10 to the power 23. There might be some typographical mistake. Not typographical mistake, just it must be 10 to the power 23. Okay, quanta. So therefore, I have written 1 Einstein is equal to n h nu. Now I am giving the last part is some of the example. It is available any books, any internet material that you know that there may be UVA, UVB, UVC. I have not written UVA, UVB, UVC, just photon energy and wavelength range. So every time, suppose if I just want to calculate visible range 400 to 700 nanometer. So I am getting, if I take 700, so it may be 299 kilojoule, 400, 171 kilojoule. Then UV range, there are 3 range you know, UVA, UVB, UVC. So 200 to 280, maybe 598. Here very high energy is required, 1200 kilojoule. 280, 315, 379, 4 to 429, like that. I have just written a range there. So what is the summary? That to break a bond, the photon's energy must be equal to or greater than that the bond dissociation energy. Now, I have given one simple example. Now, as a homework, you can take any wavelength and you can calculate the corresponding energy. But there is a very easy solution. What is that easy solution? That you have to do nothing. There is a common factor, that means if I calculate these things with the, of course, Avogadro number and everything, so what I will get 119627. If you have a calculator, you can check it. It is a magic factor. Of course, for nanometer scale. For meter scale, there may be some difference, but just you take the values of 119627 divided by any values. You can use 700, you can 280 or 315 or 400. So directly you will get that energy. So it is a sometimes for numerical problems, for any competitive examination, such type of problems may ask. So I think you can understand these things. Now I am giving some of the example, which is very common example, like in school level or college level here, but just for clarity and novelty, I am giving such type of example, like photo dissociation of chlorine gas. You see, now this photon, and I am giving that formula, I am using 119627 divided by 242. So if you know the energy, you can calculate the wavelength. If you know the wavelength, you can calculate the energy required. So bond dissociation energy is 242 kilojoules. So we need photon whose energy is 494. So the photon, light with greater than, less than, or equal to, can produce the reactions. Ozone formation is one of the most important atmospheric reactions. So you see ozone to bond energy is 498 kilojoule. So wavelength is 240 nanometers. So lastly, because I will not discuss for college level, school level, you are just learning this thing, just to a clear-cut distinction between the history of the whole, you can understand these things, that there are two fundamental laws, and one law is very, very old, you see, 1840. So therefore, in first answer, I have seen that in early 1900 time, after the development of these Einstein's and other things. So because they actually discovered this Grothas and Dapper, first law of thermodynamics, it is a completely qualitative information. I will show some of the very good research papers, how that system is developed. So one is German scientist, Grothas, and Draper is the American scientist. Therefore, I have intentionally written they initiated. In fact, they initiated the idea. There is a complete qualitative picture. absorption of photon is necessary for photochemical transfer. There are other scientists also, Priestley and other things. I will not discuss these things. But this Rothaus-Draper law is considered as the first law of photochemistry. Now then the role of course, Einstein, then Planck, and there are so many scientists. So, in Stark, he is also a German physicist. And they separately discovered. But the time lag is 1905 discovery of the photoelectric effect, or 1916, like that. So that is the most important law, that is called the second law of photochemistry. So if it is qualitative, it is quantitative. It is quantitative. So for each photon of light absorbed by a chemical system, only one molecule is activated for the reaction. So that is called the Stark-Einstein law of photochemical equivalence. And there are large number of old research papers. If you see the research papers of the Einstein during this 1905 to 19, there are tremendous, some in other languages, the translation are available. But I am just showing one of the most important research paper of an Indian, very well-known Indian scientist, because after this discovery of the photochemical equivalence, many scientists, Indian as well as the foreign scientists, perform large number of photochemical reactions. And they all supported these concepts, and one of the most important scientists of Allahabad University, Professor Neel Ratan Dhar, and B.K. Mukherjee, you see, the year is 1926. So the importance of these subjects. Einstein's law of photochemical equivalence, and if you see these whole research paper, they have used large number of chemical reactions and published in a very prestigious journal of Royal Society of Chemistry, Transaction of the Faraday Society. And not only that, after publishing that paper, they also published another paper in American Chemical Society, Journal of Physical Chemistry, I think 1931. And you see that Journal of Physical Chemistry, again Dhar and Mukherjee. You see the title, The Applicability of the Einstein Law of Photochemical Equivalence. We have studied details the energies of 14 photochemical reactions. You see, I have shown one or two, but they have studied 14 photochemical reactions. From the results now obtained, as well as by the critically examining the literature on the subject, it becomes apparent that the Einstein's law, there are some equivalence fails in the majority of the photochemical reactions. And there are then there are some further developments and other things. And there are some discussions and other things. Although they supported this law, but there are some loopholes. Then discovery of the classical mechanics and quantum mechanics, and there are so many other things. But this is the starting point of the photochemistry. Therefore, I have written, it is a first part is the fundamental of the photochemistry. Very simple phenomena, the difference between, I should not say the difference, they are all interrelated. Photochemistry as well as the spectroscopy, interaction. In my second lecture, in part 2, I will discuss the Einstein treatment of the absorption and emission. This will be my second lecture, because there are certain derivation. Here I will do some derivation, and you will understand that what is the relationship between Planck's back body radiations and why classical mechanics fails, and then what is the modern theory of quantum mechanics and other things. Thanks.